All right, howdy. Can you guys hear me? Type in live chat if you can hear me. Awesome. Okay. So, today we are going to start talking about determinants. So, last class at the very end, I went through with you guys the derivation of the 2 by 2 determinant. But I want to do it one more time just because it has a lot of ideas that are very fundamental in it. So, suppose you have a 2 by 2 matrix. So you have A11, A12, A21, and A22. And what you want to do is you want to basically try to understand what happens if you perform row reduction to this. Now the thing is, we're performing row reduction in the abstract, so we're treating these like variables. So if we were to perform row reduction, the first thing we would do is we would set row 2 equal to row 2 minus A11 minus A21 divided by A11 times row 1. And here I'm explicitly assuming that A11 is not equal to 0. And if we do that, what we get is we get an A11 here, an A12 here, a 0 here because we specifically designed this to be 0. And right here, we're going to get an interesting looking fraction. It'll have an A11 in the denominator. And it will have A11 times, oh, no, sorry. It'll have an A11 times an A22 minus an A12 times an A21. And this expression to you should be familiar. In fact, you probably encountered it if you took multivariable calculus before. So A11, A22 minus A12 times A21. This is called the 2 by 2 determinant. And here's the key fact. The matrix A is non-singular if and only if the determinant of A, which we write like this, is not equal to 0. And, well, let's see why this is true. Going up here, again, we're assuming that A11 is not equal to 0. If we assume that the determinant is also not equal to 0, then this whole expression is not equal to 0. So we can take the second row here, and we can use it to cancel out this term here, and hence put the matrix in strict upper triangular form. And if we want, we can kind of divide out by all these coefficients to have 1s on the diagonal. So non-singularity is tightly tied with the vanishing of this expression. Here's what we would like. We would like to generalize the determinant to higher order matrices. So the first thing we might try is we might try to go to the 3 by 3 case. So let's do it. So in the interest of not writing a million things, I'm going to actually kind of copy and paste the diagram from the book and just walk through it. So let me go down here. So I'm going to start with this matrix right here. Here's our goal. We have this matrix A, and what we want to do is we want to find some polynomial expression in terms of the coefficients, such that if the expression is 0, then the matrix is singular, and if the expression is non-zero, then the matrix is non-singular. So let's look at this 3 by 3 matrix. Well, the first thing we can try to do with it is we can try to imitate what we did in the 2 by 2 case. So we're going to set row 2 equal to row 2 minus A21 divided by A11 times row 1. And we're also going to set row 3 equal to row 3 minus A31 divided by A11 times row 1. And the effect of doing both of these row operations is that we're going to make this term cancel and this term cancel. And in order to even do them, we're kind of implicitly assuming that A11 is not equal to 0. But that's fine. So if we do both of these operations, we're going to get this. Let me go up here and over here. Okay. So look what happened by performing these operations. We now have an A11 here, and we have some really interesting stuff happening in this 2 by 2 block. So here's the key fact. A will be non-singular if and only if this block is. So here's why this is true. If A11 is not equal to 0, which we're assuming, then we can perform this operation, and we're left with this matrix. But then what we could do is we could do the same process that we did in the 2 by 2 case. And we could subtract off some multiple of the second row from the third row, and we could get it in strictly upper triangular form. And basically that will only work if there's some polynomial expression in terms of these entries that doesn't vanish. In fact, it's very easy to derive what it is. So let me take it over here, and let's write it down. So what we want to do is we want to look at the determinant, the 2 by 2 determinant of this block. And the 2 by 2 determinant of this block is going to be, so I'll have an A11 squared in the denominator. And then I'll have A11, A22, minus A21, A12, times A11, A33, minus A31, A13. And then minus this times this, so A11, A23, minus A21, A13, and then times A11, A32, minus A31, A12. And we can ignore the thing in the denominator, and we can focus on this. This thing right here will turn out to be the determinant of a 3 by 3 matrix. And to walk you guys back to the derivation again, the reason this thing tells you whether the matrix is non-singular is because it precisely corresponds to whether this square block right here, this 2 by 2 square block, is non-singular. But then the original matrix A is non-singular if and only if this little square block is non-singular, just because they're related by these two row operations. So you look at this expression, and the thing you wonder about it, first off, is you wonder how the hell are you ever going to remember it? Because it's a bit deal more complicated than the one for the 2 by 2. And here is the unfortunate fact. Although the determinant is easy to compute, as we shall see, the actual polynomial expression is very big. So we want a kind of generalized formula for, or even a generalized algorithm that will allow us to compute determinants. And it should recover the 2 by 2 case that we started with, and the 3 by 3 case, which we just did. But it should also tell us about the n by n case, whenever we're working with an n by n square matrix. So that's our next goal. So define a general formula / expression / algorithm for computing the determinant of an n by n matrix. Okay, so in order to do this, we have to introduce some ideas. Okay. So, the idea we're going to introduce right now is the idea of the minor of a matrix. So, let me write down a matrix. Say A is equal to A11, A12, A13, A14, A21, A22, A23, A24, A31, A32, A33, A34, and finally A41, A42, A43, and A44. This is a 4x4 matrix. And I'm going to associate to this matrix A a variety of other matrices. Here's how it's done. So given I and j, where we're going to say I and j here is between 1 and 4, just because we're using a 4x4 matrix. The matrix Aij is the 3x3 matrix obtained by deleting the ith row and the jth column. So let's do a specific example. Let's take my abstract matrix here, and maybe let's try to compute A23. So I have my A, and what I want to find is I want to find A23. Well, how do I do that? According to this, Aij is obtained by deleting the ith row and the jth column. So I want to delete the second row and the third column. So let's circle them, or actually just underline them maybe. I want to get rid of this row and this column. So there's an easy way to do that. I can just circle all this stuff and delete it. And by doing that, I now have a 3x3 matrix. Oops. So this shows you how you can compute these Aijs. Let's do one more example. Let's suppose I'm looking at a 5x5 matrix. So say M is equal to 2, 7, 8, 1, 2, 9, 4, 6, 3, 8, 0, 2, 2, 1, -5, 10, 4, 2, 1, 1/2. Oh wait, I need one more row, so maybe 0, 3, 4, 3, 0. So I have this matrix M, and I want to compute M, 1, 2. If M here is a 5x5 matrix, M12 is going to be a 4x4 matrix, and it's going to be obtained by deleting the first row and the second column. So I can do that simply by taking this, maybe moving it down here, and circling the stuff I want to get rid of. So first row and second column. Okay, that didn't work out exactly as planned. Let me try to lasso it again. Get rid of that. Get rid of that. And so after I delete that and that, I have a 4 by 4 matrix. And this right here is precisely M12. So you can see how these constructions work. The entries in the subscript basically tell you what you need to get rid of. So now we can state the general case. In general, if M is an n by n matrix, and I and j are between 1 and n, then mij is obtained by deleting the ith row and the jth column. So we're going to be using these things a lot, so we're going to give them a name. In fact, they have two different names. So mij is called, well, sometimes it's called the ijth minor. Other times it's called the ijth cofactor. And so as I go throughout this class and the next few, I will use both these names because some theorems use one of them, some theorems use the other. So now that we've introduced these things, the next thing to ask is, what is the relevance of them to determinants? Here's the relevance. So let me go over here and get you guys the actual definition. Oh, crap. There's just one more thing I have to explain. I forgot the book does it like this, but ignore what I just said here. This is not quite the ijth cofactor. It's very much related to it. Here's how they define the ijth cofactor. So you start by defining mij. And what you have to do is you then look at the determinant of mij. So you set aij to be equal to -1 raised to the I plus j times the determinant of mij. And this is the ijth cofactor. So they're related. I was brain farting. Okay. So let me walk you guys through an example that illustrates both these notions. I'm going to look at a 3 by 3 matrix. So my 3 by 3 matrix will be 5, 4, 3, 1, 2, 6, 7, 8, 9. So this will be M. And what I want to do is I want to compute these various cofactors. Here's how the process runs. First, let's look at, say, the cofactor M11. Or, I'm sorry, the minor M11 and then the associated cofactor A11. And then we will look at the minor M12 and the associated cofactor A12. And finally, we'll look at the minor M13 and the associated cofactor A13. So in this case, M11 is obtained by deleting the first column and the first row. So all that's left over is 2, 6, 8, 9. So we'll put that right here. And then M12, well, what you do is you take the first row, second column, you delete them, and what you're left with is 1, 6, 7, 9. Then the next step is you look at M13, you delete the first row, third column, and you're left with 1, 2, 7, 8. And so now we've computed the 1-1 minor, the 1-2 minor, and the 1-3 minor. And now we can compute the associated cofactors. So the associated cofactors are computed by looking at the associated minor, computing its determinant, and then multiplying it through by this sign, where it's -1 raised to the ij. So in this case, we're going to be using the sign -1 raised to the 1 plus 1, which is equal to 1. Here we'll be using -1 raised to the 3, and here we'll be using -1 raised to the 4. This is 1, this is -1. Now that we have these signs, the other thing we have to do is we have to compute the determinants of these matrices. So, the determinant of M11, well, it's going to be 2 times 9, so 18, minus 6 times 8, and then times the sign, which in this case is +1. And then we're going to do the same for A12. The determinant here is 1 times 9 minus 6 times 7. And then we multiply through by the sign, which in this case is -1. And then finally we can do the same thing for A13, which we put a 1 here, and we compute the determinant of this matrix, so 8 times 1 minus 2 times 7. So we have computed 3 different cofactors of this matrix. In fact, this matrix has 9 different cofactors you can compute according to every different choice of I and j. Let's do one more example. Suppose I take my matrix M here to be 4, 7, 2, 0, 1, 3, 0, 0, 4. This time I want to compute the cofactors A11, A21, and A31. Well, I'm going to compute them according to the formula, so I'll bring it over here. And computing these cofactors amounts to computing the determinants of various minors. So I'm going to need the minor M11, the minor M21, and the minor M31. So the minor M11 is obtained by deleting first row and first column. So you're left with 1, 4, 0, 3. The minor M21 is obtained by deleting the second row and the first column. So you get 7, 2, 0, 4. And the matrix M31 is obtained by deleting the third row and the first column. So you're left with 1, 3, 0, 4. Let me position that so I can actually see what you guys type. Now, what we want to do is we want to compute the cofactors themselves. So to do that, we have to also compute the signs. In this case, we're going to be looking at the sign -1 raised to the 1 plus 1, which will just be 1. We'll also be looking at -1 raised to the 2 plus 1, which will be equal to -1. And we'll be looking at -1 raised to the 3 plus 1, which will be equal to 1. Now we can compute all of these things. Wait, did I do something wrong? Sorry, my bottom cofactor is incorrect. Or my bottom minor. My bottom minor should actually be delete third row, first column, so 7, 2, 1, 3. And these are both correct. This is correct. So now I can compute the cofactors themselves. A11, we're going to obtain it by taking the determinant of M11 and multiplying it through by +1. So 1 times 1 times 4 minus 3 times 0. A21, we'll obtain it by multiplying through by a -1, and we'll have 7 times 2 minus 0, or actually 7 times 4 minus 0 times 2. And then finally, A31 will be obtained by multiplying by 1 the determinant of this matrix, so 7 times 3 minus 2 times 1. Okay, so I've now computed these 3 cofactors. Now that we've discussed minors and cofactors, we can kind of connect them back to determinants. And here's the connection. The n by n determinant of a matrix A may be defined as the following sum. So it's going to be A11 and then times big A11, the corresponding cofactor, plus A12 times big A12 plus ... A, you go all the way out to A1n times big A, A1n. I should specify that this is an n by n matrix. So when you first look at this definition, it's a little curious because it's defining the determinant in terms of cofactors. But then cofactors are themselves defined by determinants. And so the first thing you might ask yourself is this definition circular? And my question for you guys is, why isn't this definition circular? Maybe answer in live chat, if you have any idea. So here's the question. Anyone have a guess? Okay, so let me explain why it isn't. So right here, we're defining the determinant of an n by n matrix. The A12, or the A11s, these things, I guess I should specify, the cofactors. The cofactors appearing here in the sum, these involve the determinant of an n by n, or I'm sorry, of an n minus 1 by n minus 1 matrix. So the determinant here, well, it is expressed in terms of determinants of smaller matrices. So it's not circular, it's inductive. So here's the idea. If you have a notion of a determinant for n minus 1 matrices, n minus 1 by n minus 1 matrices, then you actually get a notion of a determinant for n by n matrices. And you get it via this sort of formula right here. And this formula goes by a name. And this is called the cofactor expansion. Expression of the determinant. So let's see how it works in practice. I am going to take a matrix, say 5, 2, negative 1, 3, 7, 8, 2, 9, 1. This will be my A. Actually, I'll call it M just for safety. And what I want to do is I want to compute the determinant of M. Well, right now we have two ways to compute this determinant. Either we could use the formula we derived at the beginning of class, namely this ugly thing, or we can use the method we just learned. So let me put that method here so you guys can see it as I execute it. So I am going to compute it using the method we just learned, which means I'm going to express it as A11 times the cofactor A11 plus A12 times the cofactor A12 plus A13 times the cofactor A13. And this means I need to compute each of these three cofactors. So we'll do that calculation over here. To compute A11, I need to know what M11 is. To compute A12, I need to know what M12 is. To compute A13, I need to know what M13 is, or these are the associated minors. Well, M11 is obtained from M by deleting the first row and the first column. So I'll have 7, 8, 9, 1. Down here I'll have, so this is first row, second column. So I'll have 3, 8, 2, 1. And then finally, first row, third column. I will have 3, 7, 2, 9. Now, I have to compute the associated cofactors. So the sign here is going to be 1. Sign here will be -1. Sign here will be +1. So I have to compute A11, A12, and A13. +1, -1, +1. Now I compute the determinant of this matrix. Well, it will be 7 times 1 minus 8 times 9. So what is that? 8 times 9 is 72. So subtract 7, you get -65. It's -65. And if at any point during this my arithmetic is off, please correct me. Now I have to compute A12. I know what the sign is over here, so I just have to compute the determinant of this matrix. So 3 times 1 minus 2 times 8. So this will be -13. And then finally I have to compute the determinant of this matrix. So 3 times 9 is 27, minus 2 times 7, which is 13, which is 14, which means the difference is 13. All right, so I've computed these quantities. This is +13. This is also +13. And this is -65. And now that I know what these cofactors are, I can use them to compute this determinant. This determinant right here will be equal to 5 times -65 plus 2 times 13 plus -1 times 13. So you can see right away that we're able to use this expression to compute the determinant of a 3x3 matrix in terms of determinants of a 2x2 matrix. Let's go up one more dimension and look at a 4x4 matrix. So now I'm going to take my matrix M here to be this thing. So I'll have a 4, 3, 2, 1, 0, 0, 1, 3, 2, 4, 0, 8, 0, 0, 1, 5. I want to compute the determinant of M. In order to do that, I'm going to use a cofactor expansion, and I'm going to express it in terms of 3x3 determinants. So the determinant of M here can be written as 4 times A11 plus 3 times A12 plus 2 times A13 plus 1 times A14. So I'll be in a good position to know what this determinant is if I can compute all 4 of these cofactors. So let's start by looking at A11. I obtain A11 by doing a cofactor expansion. I obtain A11 by first looking at the 1,1 minor. The 1,1 minor is 0, 4, 0, 1, 0, 1, 3, 8, 5. And now what I can do, actually, do I want to make my life easier? I do want to make my life easier, otherwise I'll be doing computations for days. I'm going to replace this 4 with a 0, which means in this minor over here, I'm replacing this 4 with a 0. So now I've computed the minor M11, and I want to try to compute the cofactor A11. Computing this cofactor, well, A11 is going to be equal to -1 raised to the 1 plus 1 times the determinant of M11. Now, I'm going to try to compute the determinant of M11 in terms of its own cofactors. So, the determinant of M11 can be written as 0 times the determinant of this square matrix. And I'm going to use the notation that you guys learn in vector calculus, where a determinant is sometimes denoted by a matrix with bars around it, like this. A, B, C, D is equal to AD minus BC. Then the determinant of M11 here, by its own cofactor expansion, is 0, 8, 1, 5 minus 1 times the determinant of 0, 0, 8, 5, and then plus 3. Maybe I want to zoom out slightly. Plus 3 times the determinant of 0, 0, 0, 1. And you can check that each of these 2 by 2 determinants, well, this 2 by 2 determinant and this 2 by 2 determinant are equal to 0. On the other hand, we have a 0 here. So if we compute this whole expression, we find that the determinant of M11 is equal to 0, which means A11 is also equal to 0. So over here where we had A11, we can replace it by a 0. Now we have to compute A12, A13, and A14. As you can see, this computation is really kind of nasty, but it's worth doing at least once. So now that we know what A11 is, we have to figure out what A12 is. To figure out what A12 is, I'm going to look at the minor M12. This minor is obtained by deleting the first row and the second column. So I'm going to have 0, 1, 3, and then 2, 0, 8, and then down here I'll have 1, a 5, and a 0. And in order to compute A12, I have to compute -1 to the 1 plus 2 times the determinant of M12. Now I can compute the determinant of M12 by doing its own cofactor expansion. The determinant of M12 is going to be equal to, let's see, 0 times the determinant of 0, 8, 1, 5 minus 1 times the determinant of 2, 8, 0, 5 because this corresponds to deleting the first row and second column of M12. And then plus 3 times the determinant of this matrix, or the matrix you obtain from this by deleting first row, third column. So 2, 0, 0, 1. And if I run through this calculation, I see that this is 0. This determinant here is 10. 10 times negative 1. So negative 10 plus 3 times 2. So this is precisely going to be negative 4. So the determinant of M12 is negative 4. And the cofactor A12 is going to be negative 4 times negative 1. So negative 1 times negative 4 is equal to 4. Now we can go back here and we can replace A12 with 4. The next step is to compute A13. So to compute A13, I have to look at the minor M13. This minor is obtained by deleting first row, third column. So I'll have 0, 0 here, 3, 2, 0, 8, 0, 0, 5. And A13 is going to be defined to be negative 1 raised to the 1 plus 3 times the determinant of M13. And I'm going to compute the determinant of M13 by performing a cofactor expansion on M13. So I'll have 0 times the determinant of the matrix obtained by deleting the first row and the first column. So 0, 0, 8, 5 minus minus 0 times the determinant of the matrix obtained by deleting the first row, second column. So 2, 8, 0, 5. And then plus 3 times the determinant of the matrix obtained by deleting first row, third column. So 2, 0, 0. And this determinant is the only non-zero one, but it's multiplied by 0. This is multiplied by 0, and this determinant is 0. So this whole expression ends up being equal to 0. This allows us to finish computing the cofactor A13. So A13 is going to be equal to positive 1 times 0, which will just be 0. So I can go all the way back here and I can replace the A13 with 0. The next step is to compute A14. So to do this, what we're going to do is the same general process. We're going to use the fact that A14 is equal to negative 1 raised to the 1 plus 4 times the determinant of M14, where M14 is the minor obtained by deleting first row, fourth column. So 0, 0, 1, 2, 0, 0, 0, 0, 1. To compute the determinant of M14, I'm going to inductively perform cofactor expansion on M14. So this will end up being equal to 0, corresponding to this, times the determinant of this, 0, 0, 0, 1, minus 0 times the cofactor, or the determinant of 2, 1, 0, 0, and then plus 1 times the determinant of this square block. Now if you compute this, you can see that this determinant is 0, this determinant is 0. This determinant here is not 0, but it's multiplied by 0. So you get 0. So A14 is equal to -1 times 0. And this is just equal to 0. So we can go all the way back here and note that we have everything we needed to compute the determinant of M. So this term, and this term are all 0, and the only non-zero term comes from this. So we're able to conclude that the determinant of M is equal to 12. This, as you may have noticed, is an incredibly laborious process. Basically, you start with an n by n matrix, and then you have to look at n minus 1 by n minus 1 matrices, and you have to compute the determinants of all of those. To illustrate how complicated this process actually is, let me draw a picture. Suppose you have an n by n matrix A. What you want to do is you want to compute its determinant. And in order to compute its determinant, you have to compute the determinants of M11, the determinants of M12, blah, 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 all the way up until the determinants of M1n. Now, here we have n minus 1 by n minus 1 determinants. And for each of them, we must compute n minus 1 times n minus 2 by n minus 2 determinants. Because each of these n minus 1 by n minus 1 matrices has their own cofactor expansion. And the cofactor expansion involves n minus 1 terms. So, roughly, the cofactor expansion involves computing n factorial subdeterminants of a matrix n, or of a matrix A that is n by n. And this grows faster than any exponential. And if you recall, or if you haven't seen it before, n factorial is equal to n times n minus 1 times n minus 2, blah, 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 all the way until you get down to 2 times 1. So this is a massive number, and it's a number that grows very, very quickly. Okay. So now that we've given a definition of the determinant that works for n by n matrices, what we want to know is there a faster and better way to compute determinants? Because right now we have two very, very ugly ways. One way is the cofactor expansion, which we're taking as the definition. The other way would be to kind of go back to the example we started with at the very beginning and go through this kind of abstract row reduction calculation to get these nasty polynomial expressions. And neither of these are going to be very effective. And so we need something better. And there will be something better, and we're going to start working towards it. Before we do, I want to state some special cases where the determinant is actually easy to compute using cofactor expansion. So let's start with this result. Let's suppose that A is an n by n triangular matrix. Then the determinant of A equals the product of the diagonal elements of A. So let's say our matrix M looks like this. We have A11 here, A12 here, blah, 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 A22 here, blah, 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 all the way down to ANN and A1n up here. And then everything below the diagonal is 0. So what we want to do is we want to show that the determinant of M is equal to the product of the elements on the diagonal. So it's equal to A11 times A22 times blah, 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 ANN. So this is actually a result that's very easy to prove using cofactor expansion. To do it, we're going to need the following fact, which we're going to state without proof. Let's see. Did I have it in here? I should have it in here. The crucial fact we're going to use is that if we have any n by n matrix, we can compute the determinant of it using any row or column. So we can perform cofactor expansion anywhere. Up until now, we had been performing cofactor expansion on the first row, but in fact, we can perform cofactor expansion on the columns as well. And that's exactly how we're going to prove this. Because look what happens. If we perform cofactor expansion on the first column, we're going to get the determinant of M is equal to A11 times the determinant of A11 plus 0 times the cofactor A21 plus blah, 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 plus 0 times the cofactor AN1. So these terms are all 0. So the only thing that survives is the A11 times the cofactor A11. So we can compute the determinant of M by computing the cofactor, which is essentially just going to be the determinant of this submatrix. And the reason this is true is because A11 here is equal to -1 raised to the 1 plus 1 times the determinant of M11. So this right here just ends up being equal to A11 times the determinant of M11. And by induction, the determinant of M11 is going to be equal to A22 times A33 times blah, 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 ANN. Okay, so let's show how we can use this theorem in practice. Suppose we look at the matrix 5, 7, 200, 0, 3, 4000, and 0, 0, 5. So this will be my matrix M. I could try to compute the determinant of this by going directly from definition, but I can also just use the theorem we just proved, which tells us that the determinant of M here is going to be equal to 5 times 3 times 5. So it's very, very useful. And let me illustrate one other thing. The fact that we're able to kind of perform cofactor expansion on any row or any column has one other really significant consequence. So, suppose the matrix A has a row. Maybe it's the ith row. And it's going to consist of all zeros. Then, by performing cofactor expansion, we see that the determinant of A can be written by using a cofactor expansion along the ith row as 0 times A I1 plus 0 times A I2 plus blah, 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 0 times A IN. And this, of course, will just be equal to 0. So this is one of the beauties of this cofactor expansion, is that we can do it about any row or column. In particular, if we have a row that consists of all zeros, we can do a cofactor expansion about it, and we can see that the determinant of the matrix actually has to be 0. And so let me state this result in its general form. So let A be an n by n matrix. If A has a row or column consisting entirely of zeros, then the determinant of A is equal to 0. If A has 2 identical rows or 2 identical columns, then the determinant of A is also equal to 0. Now, we've proven 1. We haven't proven part 2. Part 2 is a little more subtle. I'm going to explain part 2 by example. So maybe we'll look at a 3 by 3 case. So, actually, maybe I'll prove this in generality because it's not that bad. Suppose the ith and jth row of A are identical. And that the theorem is true by induction. What I mean by this is that it's true for all smaller matrices. So true for all n minus 1 by n minus 1 matrices. Then we can do a cofactor expansion along any row that is not I or j, and all the cofactors will involve matrices with 2 identical rows. And hence will vanish. So this completes the proof of part 2 here. Again, the proof is less interesting to me, or at least should be to you guys, than the fact that this enables you to kind of quickly compute certain determinants. Let me show you. Suppose we look at a matrix M and say our matrix M is something like this. 2, 4, 6, 1, 1, 1, 1, 1, 1. Well, here we have 2 identical rows. We could naively try to compute its determinant in terms of a cofactor expansion, in which case we'd see that the determinant of M would be equal to 2 times the determinant of this thing, minus 4 times the determinant of this thing, plus 6 times the determinant of this thing. But then this, and this, these are all equal to 0, so the determinant of M is equal to 0. On the other hand, the previous theorem tells us right away, without doing any computation, that because M has 2 identical rows, the determinant of M is equal to 0. So these 2 results, theorem 2.14 and theorem 2.13, these are the only cases where cofactor expansions can be quickly computed. Okay. Now, I suppose I should say one more thing for today. Here's a fun little fact. The determinant of A is equal to the determinant of A transpose. Let's see why this is true. Well, I can compute the determinant of A by basically writing this as A11 times the cofactor A11 plus A12 times the cofactor A12 plus blah 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 A1n times the cofactor A1n. And I can also assume the statement is true for n minus 1 by n minus 1 matrices. Then, this expression right here is the same thing as A11 times negative 1 to the 1 plus 1 times the determinant of M11 plus blah 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 A1n times negative 1 to the 1 plus n times the determinant of M1n. And because I'm assuming the statement is true for all n minus 1 by n minus 1 matrices, I in fact have that this is equal to A11 times negative 1 to the 1 plus 1 times the determinant of M11 transpose plus blah 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 plus A1n times negative 1 plus n times the determinant of M1n transpose. And this is actually just the determinant of A transpose, because this is a cofactor expansion of A transpose along the first column. So if you recall that basically A transpose is obtained from A by kind of flipping the rows and the columns. What this calculation shows is that the determinant of A in terms of a cofactor expansion along the first row is literally the same thing as doing a cofactor expansion of A transpose along the first column. So this is very, very intuitive. Anyways, next class, we're going to start using these results we proved towards looking at far more effective and quick ways of computing determinants. So office hours are starting now. I will be here if you guys want to ask any questions. I will have new homework posted later today. All right. So good luck and enjoy the rest of your day.